Okay, we're going to start now. Okay, good morning, everyone. I am delighted to welcome you to our fourth Tech Talk 2023, AIEI X NVIDIA. You are with me, 𝒑𝒓𝒂𝒊𝒏𝒊𝒏𝒈, or you can call me Dwight. I am a moderator of today's talk. Let me tell you a little bit about our series of the Tech Talk. This talk will provide you with a special opportunity to get knowledge from international professionals who give you the functional language you need for real life and hands-on tasks in the technical, industrial, and scientific fields. Right now, we are glad to bring you to our fourth Tech Talk series of 2023 on the topic of efficiently pre-training large language models and fine-tuning for downstream tasks. Our today's speaker is a developer relation manager at NVIDIA Asia Pacific South region. After his PhD in applied mathematics in the University of Namur, Belgium, he joined the Smart Infrastructure Facilities of the University of Wollongong, Australia, where he was a lecturer and the head of Digital Living Lab researching and developing AIoT solutions, focusing on the development of new applications of AI and embedded IVA for smart cities and environmental monitoring. Being passionate about applied AI and how to accelerate with GPUs. He is now a developer relation manager at NVIDIA, helping developers and scientists in their journey to build the next generation of AI-based solutions, with a particular focus on conversational AI. Without further ado, everyone, please welcome Dr. Johan Barthélemy.
Thanks a lot for the very kind introduction. It's my pleasure to be here with you and to be able to present about one of my favorite topics, which is all about large language models, how to pre-train them and how to fine-tune them for downstream tasks. So let me share my screen so we can get started. Yeah, share. All right, so I hope you can see my screen now. If you don't see it, just shout. Perfect. All right, so I'll try to make it quite high level. So I'd like to give you some details, a feeling of how it works, but without going too much into the equations and the mathematics, even though I'm an applied mathematician. So I'd like to start with a bit of a refresher of what are large language models, right? So out of the box, large language models is something that has bigger to trillions of parameters. So those are artificial neural networks, a bit similar to the one you're probably used to or familiar with in computer vision. But instead of having a few million parameters, you can have up to trillion parameters. That gives you an idea of the size. And they are typically trained on very, very large data sets as well. So for ChatGPT, one of the most popular models, it has been trained on more than 45 terabytes of data. Basically, we download most of the public internet and put that into a data set. Those large language models, they can be used for so many different applications, like translation, text generation, content generation, like code or image or even video, and they are able to generalize, right? So the bigger the model, the more generalizable it becomes and the more tasks it's able to do. So it's becoming very, very popular, and I'm sure that you heard about ChatGPT, which is probably the most famous one at the moment. It's one of the models that triggered a revolution, and it's only a few months ago, not even 6 months ago. It's an advanced chatbot, and which you are able to interact with in a very natural way. So you can just ask it questions like you would ask your friends or your family, and it will give you answers. Those answers will be grammatically correct, and you can have sometimes good facts, but you need to be a bit cautious about what it tells you, right? It's an AI. That model relies on GPT 3.5. So basically, that's GPT 3, but where we could put a bit more training, a bit better data set, a bit more refinement. Okay, but everything I'm going to show you today will actually allows you to build something similar to ChatGPT that has been designed by OpenAI. So first of all, you can ask yourself, why do we want large models? What's the point of making things so big, right? Well, it turns out in deep learning that the bigger the data set, the more performances you can get, the more accuracy you can get, right? So that's the point of the graph above there. So the x-axis gives you the training data set, but that's a logarithmic scales, and the y-axis gives you an idea of the loss of the error. And the more data you can give, the lower the error will be. And that's actually an exponential decrease, right? Because the x-axis is a logarithm scale. We are still in this area there. So at some point, well, we get to the point where it's impossible to lower the errors anymore, but you are still in this region here. The thing is, the more data you bring, the bigger the capacity of the model you need, right? So it means that you need bigger and deeper model with more parameters so that it can digest all that information. And that's the story being told by the three graphs at the bottom. So the more compute you can bring to the table, the more parameters you can handle, right? So it means that the error will go down as well. And if you've got more parameters and more compute, then it means you can also grab more data, right? So that's the point of this data set here. So again, more data set means we need bigger model to make it more generalizable and more smart. And also would like to give you an idea of the size of the models, how they are evolving for the last 10 years, right? Actually, if you look at Moore's law, it tells you that every 2 years, the compute will double. The compute capacity of a CPU will double every 2 years. So that's a blue line there. But it turns out that with the AI revolution that started with AlexNet and most of the models were done for computer vision, you can see actually that the amount of complexity is increasing by a factor of 25x. Right? So every 2 years, the complexity is multiplied by 25. And that was true up until a point here. In 2017, we got transformers model that enabled large language models, and those models have even a steeper curve, right? So every 2 years, the complexity increases by a factor of 275x. Right? And we are able to do that because we have the hardware to perform the computations, namely the GPUs, and we are also able to collect data more efficiently than before, thanks to internet, IoT, and all those accelerated databases as well. So truly, the complexity is exploding in terms of data, in terms of compute, and in terms of complexity of the models. But that's great, right? That's good news, because those large language models are actually unlocking new opportunities. You are able to create content now with those large language models. So you can use, for instance, Copilot on GitHub to help you code. You are able to ask an AI writer to write some blog piece for you. You can ask it to create some images if you are using DALL-E or Midjourney or Stable Diffusion. Of course, they enable chatbots like ChatGPT, right? So you are able to have a conversation with an AI that will give you answers to some queries. You are easily able to develop summarization engines as well. So you can give it a big textbook, ask it to summarize it in a couple of paragraphs, and boom, you get your answer. It's also able to power virtual avatars. So if you want to interact with a 3D characters in a game, now they can be powered by an AI that is able to naturally interact with you. It's able also to perform translation for you. So from French to English, or from Thai to French to Japanese, no matter the language, we've got the resources now to develop a very, very accurate translation engine, actually even better than what a human expert would do. And those LLMs, they're also very useful in the healthcare industry. So healthcare, if you want to develop new drugs, for instance, you need to understand DNA or proteins, and they can be coded as a language, right? And because they are similar to a language, we can apply the same large language models that are useful in different applications to solve those healthcare problems. To give you an anecdote, one of the vaccines for COVID-19 has been developed thanks to that kind of generative AI. So that was AstraZeneca. Right. now that you have an idea of what LLMs are, I just would like to give you an idea of what transformers are and why we'll see later. But initially, when we were dealing with language models or anything related to natural language processing, we typically relied on recurrent neural networks. Why? Because those recurrent neural networks, they are very good to model sequential information, right? So they are very good sequential models where the order of words or tokens really matter. Right? So for instance, Jane when looking for trouble is really different from trouble when looking for Jane. Right? So the same words are used in the sentence, the two meanings are different. And recurrent neural networks, they are able to make sense of the orders in the sentence. The problem with RNN, or let's say the challenge, is they tend to forget quite quickly the earlier component of a sequence. So once the AI is analyzing trouble here, maybe it forgot that it was Jane that was looking for trouble. So that's something that is a bit annoying with RNN, so a bit tricky when you play with RNNs, right? So whenever you've got a very large paragraph or a very large sentence, RNNs are not well suited for that. There are different types of flavors for RNNs, like gated recurrent network or LSTM, so long short-term memory networks. But at the end of the day, they are quite slow when you want to train them because you cannot really parallelize them. You always need to wait for the outputs of one component before you can treat the second one, right? Because in RNN, the output will be acting as the input of the next layer. So you always need to know what's happening before you can get to the next layer. So it means you need to process the model sequentially, so it's not really good for parallelism. So that's where actually LLM and transformers come into play. So large language models nowadays, they're powered by transformers. And when I mean transformers, I don't mean those robots. I mean those little beasts that you can see on the left side here, right? So transformers have been developed in 2017 by Google and the University of Toronto. They were originally designed for translation. Why? Because they can take an input, encode it, and then decode it into a different output, a different sequence. It's like you take one sequence and you convert it to a different type of sequence, but the two of them are related. So that's really a good fit for translation. Good thing about transformers is that they can be efficiently parallelized because it's just a matter of multiplying matrices. So you can use tensors and vectors and all those kind of things that are very easily parallelizable on GPUs. They've got a couple of tricks on the side. So by design, they will never forget anything because they take into account positional encoding. So you feed the whole sentence and then you add to each word in the sentence a position identifier, a positional encoding. You can train very big model with large data thanks to those two characteristics, right? Parallelization and positional encodings allow them to be trained on large data very efficiently. For instance, the original version of GPT-3, so before ChatGPT, it used 45 terabytes of data. So GPT, my bad, transformers, they are powering BERT, GPT-3, ChatGPT, T5, DALL-E, Midjourney, Stable Diffusion, all those kind of things. Okay, so that's really the basic foundation of large language models. And they've been detailed in the paper, Attention is All You Need. It's a very, very good paper. I will encourage you to read it. Now, instead of just looking at that piece and not really understanding what it means, I'd like to give you a brief overview of the architecture and how it actually works to show it's not magic. So at a very, very high level, transformer will take an input, je suis étudiant, so that's a sentence in French. That input will go into the transformer engine, and then you get an output, I am a student, right? So that's the translation into English of the French sentence, right? Remember, transformer was designed for translation. All the images I'm going to show you here, the illustration comes from that blog from J.A. Lamar. It's a very good one, so I invite you to have a look at it if you're really curious about transformers. Okay, so let's open the transformer engine now. So you got your input, and actually the input will go through a sequence of encoder. The encoder will actually map the input to an embedding, so a representation of the input. Send that to the decoder, and the decoder will actually send that encoding into a new sentence, a new sequence. I am a student. So you can see there is plural here, encoders and decoders. So actually, each block can be seen as a sequence of encoders here and decoders there. So the input will go through a sequence of all those decoders, and at the end, when we reach the last encoder, we go to our final embedding, it's going to be passed to all those decoders. And the decoder will actually treat the sentence one word at a time, right? So let's have a look at what an encoder block is. The encoder is actually a sequence of two models. You've got self-attention, and then it's followed by a very simple feed-forward neural network. So self-attention, that's one of the magic ingredients of transformers. Self-attention means that it's able to create attentions between the words in the input sequence. So it can look at the relationship between all the words inside the input sequence. So here, if we go to input, the animal didn't cross the street because it was too tired, we can have a look at which token or word it is related to. So it, in this particular case, is related to the animal. That's why you've got the strongest association or relation. So that's what attention does. It tries to find what are the relations between the words. And those relations, those attention, they are self-learned by the model. Right? They all come from the 𝐓𝐞𝐜 matrices that we could see before. So we can have one head, so it means we got one attention, but we can actually expand that. We could have two heads attention, right? So it is not only related to the animal, but if you look at the second attention head, it will be also related to tired, right? That's the verb there. So we've got two heads here, but you could expand that ID to 3, 4, 5, 10 heads. And all those heads can be generated in parallel. Right? So it means it's very good for parallelization and good to be put on a GPU. On the other side, you've got decoder, right? So decoder also has self-attention and a feed forward, but in between, we've got what we call an encoder-decoder attention. So we are going to look at the relation between the input and the output. Okay, so we've got the input here in French. L'accord sur la zone économique européenne a été signé en août 1992. And you've got the output in English. The agreement on the European Economic Area was signed in August 1992. So you've got an attention matrix, and the brighter it is, the more attention or the more the stronger the association is between the words, right? So accord and agreement strongly related, right? So you can see that most of the attention is on the diagonal because most of the words follow the same sequence or the same order between English and French, except for this particular area here. Here, French actually swapped the order of the words. We got zone économique européenne, while in English that would be European Economic Area. So that's the opposite. So that's why you've got this thing here, right? So the attention, so the encoder-decoder attention is able to look association between input and output. That's very important. All right, so how does it work? We've got our input sentence, je suis étudiant. So 3 words. The first thing we do is we map those into an embedding. So embedding is a way to actually convert a word into numerical coordinates. Okay, that's embedding. You've got an example here on the bottom right. If we had an embedding in 2 dimensions for animals, you could have an x-axis for domestic versus wild and a y-axis for small versus big, right? So you want the animals with the similar characteristics to be close to each other, and the ones that are not similar at all to be very far apart, right? So if you look at domestic and small, you could have kitty there. But now if you've got something big and wild, you can have a giraffe. If you have a dog, that's probably going to be smallish and domestic as well, right? So the goal is to take a word and map it into an embedding. It can be any number of dimensions. And that embedding is also something that is being learned by the network. You don't need to input it yourself. So once you got embedding, it goes to the self-attention, right? We're going to look at the attention between the different input token. That's going to be mapped into some vectors there, and then you put that into feed forward. And at the end of the feed forward, you will have actually a new embedding. So it's just a linear transformation if you want. And that's going to be fed to the next encoder afterwards. So the good thing is each word here follows its own path. So it means that it can be parallelized again. So very, very fast, very, very efficient. As I mentioned, when it's done, the encoder will send its output to the single encoder and we repeat the process. Okay. Another thing I'd like to mention before we move on is that transformer architecture is also does not forget about words, right? Why? Because you use positional encoding. So we know we associate with each token or each input its position in the sentence. So that position can be seen like an embedding, and it's something you can choose arbitrarily, or it can be also learned. So you just need to make sure that the word that comes in the first position has a particular coding. Then the second will have a second coding, the third one will be a third coding, etc. So we always know that the embedding that is associated with this encoding will be always the first one. That's how we remember the location of the token in a sentence. So those can be done by a function. So it's very easy to actually extrapolate to any number of dimensions. The only thing is the dimension of the position encoding should be the same as the embedding. That's why if you've got an embedding of size 4, you need to have 4 components for the position encoding. And you just need to addition them. So very simple. And here you've got finally the full overview of the transformer, right? So you've got the inputs at the bottom. You have the positional encoding that you add to the words embedding, goes through the first encoder. So you got self-attention, and then you can go also to some normalization step. Then you got the feed forward and the normalization. So the normalization is only added to speed up and help the training process later on, right? So once you've got through that encoder, you can go to the second encoder. Then the output of the final encoder is being fed to the decoder, right? So we've got decoder 1, that's the same thing, self-attention, normalization, encoder, decoder, normalization, feed forward, and then got again a normalization step there. Then you can go to the second decoder, then you've got the linear and softmax layer to make the classification step. So that's where we're going to predict which is the next word. Okay, so if we see into action now, you can see that you've got the input, je suis étudiant, goes to the embedding, and then you've got the position encoding, goes to the encoder first, and you've got our first encoded words, right? This is being fed to the decoders, and then you can predict the first token, I, right? And you've got here actually all the probabilities associated with all the words in the dictionary. And you can see that I is the one with the highest probability, so that's why I put it as an input. So that was for the first one. What we do after that is we feed I into the as an input to the decoder as well, and we repeat the process. So we just keep looking at I am a student. So very, very simple. I didn't get into the mathematics of the attention and self-attention, but if you're interested, that's all available in the paper and also in the blog post here. Now, the transformer architecture that I showed you, there was encoders and decoders, and that's how it was designed in the original paper for translation. But we found out that actually you can build model just using the encoders if you wanted to. And those architectures are very good for understanding language. So they can be used for sentence classification, named entity recognition, and extractive question answering. So you feed it a text, you ask a question, and the model will find the answer in the text, right? So the models will be typically Albert, BERT, and distilled-BERT. So really we just use the encoder part. We've got models that only use decoders, and that's the ones that are very good at text generation, like GPT-3 or GPT-2. So that's what you can see with ChatGPT as well. So we just need decoders. And then you've got the encoder-decoder. So that's the original approach, right? So that's really sequence to sequence. So you are going to generate new sentences that depends on a given input. So that's why you've got the translation model like multilingual T5 or T5. Okay. All right, so that was for the theoretical background of LLMs. Now I'd like to give you an idea of how you can pre-train those LLMs, and in particular using 𝒓𝐚𝐺𝒂𝒂𝒊𝒏𝒂𝒂💏, which is the free and open source SDK at NVIDIA that you can use for that particular task. So typically, pre-training LLMs is something that is very, very hard, or it's perceived as very hard, right? Because you've got a lot of parameters, billions of them. You've got an architecture that seems a bit complex at the beginning. So transformers, it's a lot of different layers. You can have some challenges when it comes to the precision of the computation and how to fit all those big models into memory. You have different types of ways to parallelize the model, get a bit of mathematics, those kind of things. So it can be overwhelming at the beginning. And actually, I just want to show you that it can be as simple as a 3 weeks journey to build a large model. And those 3 weeks actually will be 3 steps, 1 per week. The first one would be data preparation. Then we are going to do the pre-training, and then we can deploy it. And I'm going to show you an example to pre-train a language model for French and Spanish that contains 1.7 billion parameters. So 1.7 billion parameters might not be very large by today's standards, but it can still fit in today's modern GPUs. So that means you could try that at home. If you are more serious about LLMs, then you would look at models with 20 billion parameters, or 540 billion parameters, or 175 billion. So that's really up to you, or it depends on the size of your architecture and infrastructure. All right, let's start with the first thing, data preparation. First thing is to select a data set, right? And there are a few available publicly. For instance, you've got Common Crawl, which represents several years of crawling the internet. So that's huge. The link did not discriminate between different parts of internet, just go there and download it. From Common Crawl, actually, you can also have the pile, which is an 800 GB data set of different type of text for different types of tasks. Right, so that's available here. You've got OSCAR, which stands for Open Super Large Crawl Aggregate Corpus, which is based on Common Crawl. And you've got also data sets from Google, like the MC4-1, which is a multilingual data set. So for our context, we're going to play with OSCAR. Okay. So OSCAR, if you look at it and you just select the French and Spanish data, you will have 282 GB for French and 278 GB for Spanish. First thing we do is to do text deduplication. So we want to remove duplicates into it because you don't need those. After that, well, French was now divided by 2. So we've got 138 GB left and Spanish 151 GB left. Okay. After that deduplication, we want to do some language filtering. So it means that we want to make sure we just keep everything that has actual text and not only numbers. Then we can do some general cleaning. So we can remove some sentences or some words or things that do not have punctuation. So that's other cleaning. So that's everything you can have in mind. And finally, you can blacklist some words. So if you want to remove all the root words or the curse or everything you don't want the model to be aware of, that's why you're going to do the blacklisting. Right? So you don't want your model to be cursing at your customers. So that's why you're going to remove all those not so family-friendly words. At the end of the day, we could get a data set that is clean, and French, it's 117 GB, and Spanish, 149 GB. That cleaning process, so we provide some script to do that on the website. It took roughly 12 hours per language, and that was done using the DGX server. So that task was mostly CPU intensive. So we've got the clean data. The second thing we do is to convert it to a binary format, namely the MMAP format. Why do we want binary format? Well, you can see actually the reason why. So when it's converted, we can get a smaller memory footprint, right? So French, it takes only 51 gigs of space, and Spanish only 71 gigs. So it means that it will be faster to load into memory as well. So that's why we want a binary at the end of the day. That conversion took also a bit of time, French 40 hours and Spanish 48 hours. Now, once you've got your data set ready, the second thing you need to do is to create a tokenizer. Right? So the tokenization is the process that will take all the words into your sentence and split it component per component. So it can be, each word can be one component, okay, can be one token, but you could go also sub-words, which has advantage that if there is a new word coming into an input sequence that was not part of your original data set, then it's able to process it. So we got word piece or sentence piece, but word piece is probably one of the best ones. But also BPE piece, so plenty of options there. And typically each LLM is associated with a tokenizer. But it's a required step so that we can split an input sentence into token. So here you can see that training tokenizer is very fast, roughly 45 minutes. So NeMo Megatron allows you to do those kind of things because you provide the script. So you start with an internet scale data set that you need to download. You're going to clean it, filter it, and compress it, right? So that's why you can do the deduplication, and then finally you can use that for training. So all those steps are actually accelerated and make it easy with NeMo Megatron. We also allow the distributed processing of those steps, so that's where you can shorten the time it takes. We do data cleaning, and we can remove HTML files and JavaScript files or other things like that. Okay, so that's all the different types of tools that can be used to accelerate your data curation and pre-processing. Okay, so you worked already 1 week, you got your data set ready. Second week, it's about the model pre-training. And in this case, we're going to train something similar to GPT-3, which has only transformers. Pre-training a big model means that we need something that is able to take advantage of parallelization. Right? So we've got a very large model, so that's something that's depicted on the left, and there are a couple of ways we can actually split that model. We can split it horizontally, like that, or vertically. So the first step, when we do like that, the vertical split, so that's the pipeline or interlayer parallelism, so that will increase the throughput. Right, so we've got one GPU processing this, and then when it's done, the second GPU will process that, and then we can continue. Right, so that will maximize the throughput, because while the GPU2 is doing this part here, GPU1 can start again with this part of the neural network. That will maximize the GPU usage in a single node. Now it works okay if you can put all those things, all those layers into a single GPU. Sometimes it's not possible. So what we do is the horizontal split, which we call tensor or intralayer parallelism. So it means that one layer that you can see here is split across different GPUs. This will minimize the latency because you split this layer into 2 different GPUs. It will take less time for them to compute that particular layer. So you can minimize the latency. So when you take advantage of pipeline and tensor parallelism, you are able to actually both maximize the throughput and minimize the latency. But that's just here another way to represent what I just said. You've got the data that goes from left to right. You can split it vertically or horizontally, right? So vertically for pipeline or model parallelism, and vertically for tensor parallelism. Other things that might be interesting when you play with large language model is to reduce memory consumption. And again, I'm not going to go into the details, but what NeMo Megatron allows you to do is to play with sequence parallelism. So we are going to split the tensor across the time and sequence dimension. And we're going to reduce memory consumption of those activation tensor so that we can reduce the computation as well. Right? So we can reduce memory here. And we can also do some selective activation recomputation. So we can actually choose when we need to compute activation functions, or if we just prefer to store them. So just a detail. Let's get back to our case. So we want to do distributed training of a model that has 1.7 billion parameters and that follows a GPT-3 architecture. So you got actually 1.7 billion parameters that comes from 24 decoder layers from the transformer architecture. And we've got hidden size of 2004, sequence length 2048, and vocabulary size more than 50,000. So that's the number of different words that we have into a dictionary. Okay. Sequence length, that's the sequence for training that's the maximum length of the input. So the maximum number of words in the input. And the bottom line here, it's related to the parameters of the optimizer. Right? So when you train a neural network using an optimizer, and they relies on parameters like the learning rate, the type of decay, if you want to, the weight decay parameters, what's the init values, what's the batch size, if there is a warming sample for the learning rate. And here, you can also play with tensor parallel and pipeline parallel. So that's what we've seen before. So let's say we took tensor parallel of 2. It means that each layer will be split between 2 GPUs, GPU 0 and GPU 1. Pipeline parallel means that we don't have any split vertically. So we just have this nice split here. Okay? So that's how you would split your model if you had only 2 GPUs. If you're using a machine with 8 GPUs, like a DGX, actually you can replicate this base architecture 4 times, right? So you can use data parallel of 4. So you are going to split your data into 4 mini data sets that can be divided across those 4 replicates. Now, once you selected your architecture and your parameters, you can start training. And training such a model, it's very, very simple using Megatron, right? So you just need to write down the parameters you picked before as an argument into a command line interface. And so you've got a section here that tells you want a GPT model architecture with 24 layers and all the other things you've seen before. You define the strategy for the distributed training. Okay, so the batch size, tensor parallel, data parallel, etc. You can define the parameters for the optimizer. What's the tokenizer? So that's the thing we trained in the first week. And then you've got also parameters here for the FP16 training. So FP16 is hash precision, meaning that actually we can make the math operation twice as fast while taking twice as less memory. And doing so, you actually do not lose any accuracy. So FP16 is something that you might want to take advantage all the time it's available to you. Once you started training, you just need to sit back, relax, and wait, right? So you can just enjoy a snack, have a drink with a friend, and you wait roughly 1 week until you can see that the loss is going to the desired level here. So we had a target perplexity of 11, and it took roughly a week to achieve that. So we've got 2 lines here, one for French and one for Spanish. So perplexity, if you're not aware, is just another way to compute the loss for large language models. Once your model is ready, you can actually start playing with it, and we provide also a couple of command line interface and a couple of scripts to play with it right away. So you just need to load the model, the checkpoint, into a web server that is provided, and you can start sending requests to the model. Right, so that's what we see here. You send a curl, well, a post request using a prompt. Once upon a time, a turtle lived in, and then the model in green will actually complete the sentence for you. So once upon a time, the turtle lived in a very big garden in the middle of a forest. Every morning, she goes for a little walk, etc., etc. So the model, even though it's a small one, was able to generate something that makes sense. Here it's in French. You can ask the same thing for English, but you could train the model for the Thai language as well. So when it comes to training, actually, so that was a very high-level overview. And you made a bit of manual choice here, but Megatron also provides an hyperparameter tool to help you actually pick the right parameters and ensure convergence for you. So if you give Megatron your training constraints, saying that I've got maybe 2 weeks of time, and you give inference constraint like I want the model to give me answer in less than 100 milliseconds, given the size of your GPU infrastructure, also and different parameters, Megatron will actually recommend you the right model size. Oh, you're going to need 1.5 billion parameter, 20 billion parameter, 500 billion parameter, 1 trillion parameter. So at the end of the day, it will tell you what's best for you. Based on that recommendation, Megatron will generate the configuration for you. And you can use that configuration to train the model and use that configuration later on. It can also do the same thing for the inference. That's something we need to see later on. Okay, so the recommender engine and the config file generator, those are actually using heuristic that we provide. And the second part here will make the hyperparameter search for you as well. So as soon as it's done, that process, you can kickstart the pre-training, and you are sure, 100% sure, that you get the model trained and it's going to converge. Okay? But yeah, this step, the first one here, is optional. If you really know what you want, or if you want to make some tests, you can actually override that or bypass this step to go right away to the efficient hyperparameter search. Right, so you've finished pre-trained model. Next week is the deployment. So when you want to deploy your model, you've got a couple of requirements, right? And probably one of the first requirements will be the memory. So memory, well, as you know, the memory on GPUs is, well, not unlimited. But if we take our initial model, so we've got 175 billion parameters, for instance, knowing that we've got 2 bytes per weight because we're using half precision, and we just divide by the right number to get to the gigabyte, we end up with a number of 225 gigabytes. Right? So there is no GPU nowadays that has that amount of memory on a single board. So that can be a challenge if you want to deploy that on a single GPU. If you didn't use FP16, you would end up with a model that would have 650 gigs. So you already applied some optimization. Now, one of the first things you can do is to prune the model. So if you look at the matrices that contains all the weights, you can actually say that all the weights that are close to 0 will be set to 0. And you can actually enforce a given ratio for that. You can say, I want half of my weights to be set to 0. And all of them that are closest to 0 will be actually removed from the model. Doing so, well, you're going to remove half of the weights, right? And you're going to accelerate the compute and also lower the memory usage. That's why you can go down to 160 gigabytes. So that's already a good decrease, right? So from an original model of more than 700 gigs, you went down to 325 because you use FP16, and now you are down to 160 because you are using sparsity. You can go further, right? From FP16 that still use float, you can actually apply quantization, which means that instead of using floating point numbers, you can use integer numbers, right? And doing so, you are going to divide by 2 the amount of memory required for your model. So you can go down to 81 gigs. And that's very close to what's the maximum capacity of a GPU today, which is roughly 80 gigs. So that could fit into memory. Okay, so that's one of the advantage of using integer 8. We provide tools so that when you do the conversion from FP16 to int8, you do not lose any precision, right? The accuracy will remain the same, or very, very, very similar to what it was with FP16. Okay, so memory consumption is something we can play with. There is something else that you can play as well. It's actually the optimization of the model. So you could use the original file, but actually you can do better than that. You can optimize it using, for instance, TensorRT, which will take your trained neural network, go through a series of optimization to generate an optimized inference engine. So what TensorRT is going to do, it's going to actually see if it can fuse some layer. So instead of having 2 or 3 matrix multiplication, you can just do 1 matrix multiplication by putting everything together. If you've got some recurrent neural networks, it's going to unroll the loops there. It's going to test different kernels that's going to be depending on your GPU architecture. So if you use a V100, you get different optimization than if you use the A100 or the H100. It's going to also try to split the model into different parts that are homogeneous. So one that can be used with TensorRT, others that might need to fall back to the original framework. So there are many things that's happening there. Right? At the end, you've got a binary file that's ready for inference. In addition to TensorRT, we also have faster transformer. So faster transformer, it's a backend that is really dedicated to accelerate transformer functions, hence the name, right? So we are going to accelerate the encoder, decoder blocks and make sure that all those optimization can be used on the GPUs. Using TensorRT and faster transformer, you can get a speed up of 3x. So that's 300% faster than the original model. Once you've got your model optimized and you've got your inference engine ready, then you can start serving it, right? And you can use the Triton inference server. So Triton is, again, an open source tool or SDK that we provide that is really dedicated to serving AI models. And any type of AI models. It can be a PyTorch model, TensorFlow model, a NEMO model, a Megatron model, some regular Python code, some C++ code. But what is going to optimize is the request and the serving of the model. So you can get multiple users asking requests from one model. Triton will orchestrate it, optimize the loading and unloading of the models, and make sure that everyone gets their answer or the answer satisfied as soon as possible. So there's a lot of optimization going on there, and that's very easy to use. Now, how to take advantage of a faster transformer? Well, once you've got your model stored somewhere, it's just as simple as coding one Python script, right? That's all you need to do. You just need to add a couple of parameters to say what was the tensor parallel and data parallel and those kind of things. So that's basically one line, right? And you can even do the inference with faster transformer directly. Even though it's very nice to pair it with Triton, right? So faster transformer can be embedded into the Triton inference server as a backend. So just to show you that you can actually perform inference on multiple GPUs as well and different precision. So let's see if this works. So on the left side, you've got the output of NVIDIA SMI, which is a utility that tells you the usage of the GPU. So here you've got 8 GPUs that are V100. You can see in the column, pointer here, that's the memory being used. So for now, the model is being loaded on the first GPU. That's roughly 8 gigs of memory. And it's at rest for now, so there is no usage. The model is only preloaded. But we're going to see that we can load the model on the second GPU as well to speed up inference, and we can use different precision to lower the memory consumption. So for now, the base case is one GPU with 𝒑𝒓𝒄. Okay, so let's start. And it's going to be quite quick, but that's the bottom right. So the first inference here, is it going? Yeah, will be 13 milliseconds, right? And you can see the output was very fast for one token. Now, the second thing we're going to do is to use FP16, and we could go down to 9 milliseconds, right? So we removed 4 milliseconds from the compute. Then we use 2 GPUs, 8 milliseconds. And if we use tensor parallelism, we get down to 6 milliseconds as well. So just by playing with a couple of parameters, we can split the model across 2 GPUs or many other GPUs, and you change the precision, and that's how you can get the inference done in less than actually 6 milliseconds, which is quite huge. If you can imagine a model that has 1.7 billion parameters being processed in less than 7 milliseconds. So it allows you to create real-time application, basically. All right, so that was one thing. That's pre-trained model. So you've got a model that is able to do text generation for you. But that's not the end. Usually when you pre-train a model, you've got some ideas for downstream tasks. And that's why you've got actually all those tasks that are embedded into the natural language processing umbrella, like general Q&A, summary generation, automatic writing, auto-completion, translation, code generation, sentiment analysis, etc. So typically, you used to take a model that you pre-trained, like let's say BERT, and after it's been pre-trained, you are going actually to fine-tune the last layer. So you take the model and you're going to retrain part of it to adapt it to your task. And if you want it to do language identification, named entity recognition, and Q&A, so squad, you will need to retrain 3 different models. And it means that you need to perform gradient updates and go to the optimization process, right? So it means you need to feed it a lot of different examples. So that actually can be quite costly. BERT is quite large already, and it takes a lot of time to retrain. You need a lot of GPUs, you need a lot of data. Okay, so it's sometimes better to use larger language model instead of BERT like ChatGPT. Because those models, they can be zero-shot or few-shot learning. So it means that they can learn new tasks without a single gradient update. So you don't need to go through the optimization process again. You just need to show them what you want. So they can learn new tasks. So you train them for one particular thing, language generation, but then they can learn how to summarize or to translate. And you didn't train them to do that specifically, right? So a single model can serve many use cases. So the larger the model, so in the billions or trillions parameters, the better it becomes at serving many different types of tasks. And the goal is not to retrain those models ever again, right? So you just use few-shot learning. So what do I mean by zero or few-shot learners? Zero-shot learner, that's what you can see here. You just need to give a task description in a natural language, like English, and a question, a prompt, and then the model will generate an answer right away. Right? So you hope that the translation here will be fromage, which is the right thing for in French. One shot is you show the model one example. You've got, again, the task description, you've got an example, si auteur becomes l'outre de mer, and then you've got your prompt. And few shot, that's basically an extension of one shot. You've got the task description and a few examples, and then you get the prompt there. So how efficient is few shot learning? Well, very much. And actually, the more parameters you have in your model, the more efficient it becomes. So you've got here the output of 3 different types of model, 1.3 billion, 13 billion, and 175 billion. And x-axis is the number of examples that you show, so the number of shots. And the y-axis is the accuracy. So with zero shot, well, that's not that great. You've got less than 10% accuracy, even for the larger model. But when you give more and more numbers, and that's like here you've got 10 numbers, well, 10 shots, you see that you can reach above 60%, and you have never, ever updated the model again. The difference between the solid line and the dotted line is that in the dotted line, you don't have any prompt, right? So you don't give that first description there. In the solid line, you ask, when you give as an input the task description. Okay, so giving the task description makes a big improvement here at the beginning, but at the end of the day, when you give more and more prompt, you don't need to give the description anymore. And that's another graph showing you how efficient or how accurate the zero shot, one and few shots evaluations are, right? So for text prediction, giving a few shots allows you to reach nearly 90%, right? And it's the same trend. The more examples you give, the better the model becomes. But remember, we did not retrain the model. We just show it examples. So we just did in-context learning. So you give a prompt, like, would you say this movie review is positive or negative? You give an answer. You give a context. I love that movie. That's being fed to the LLM, which will try to generate a text similar to the input, and it will give you answer positive, right? So you just give this input, and the model will give you the answer. So if you want to try that kind of things for yourself, well, that's very easy to do. You just need actually 3 things. The Triton inference server with the faster transformer backend and a model from Hugging Face. So you can find our NVIDIA models, so up to 20 billion parameters on Hugging Face. You can download them, deploy them in Triton with faster transformer. You can start playing with that. How to do it? You just need to follow the instruction from the technical blog post. It's like a dozen lines to type into a Linux command line interface. I just wanted to show you quickly example of zero-shot learning here. So that's something for text summarization. You can see the input user. Let's see if it changed. Oops. Sorry. So you start actually to create some connection to Triton server using HTTP. You build a request saying that you want to use GPT-3 20 billion parameters. Then you can go to the summarization model here, so the zero-shot example. And the input is actually the inputs that we want to summarize. And the only thing we said to the model is TLDR, so too long didn't read. So we don't even give really a prompt here. But the model will actually generate an answer for us. Right? So that's all we need to do. Another example of zero-shot learning from the same model. So I just say, write a paragraph about why NVIDIA is leading in AI and deep learning. And it generated this sentence for me. I didn't have to do anything. So NVIDIA is leading the way with AI and deep learning. They're the first company to create a GPU that can do both graphics and deep learning, which has led them to be the leader in AI. So yeah, that's good enough for me, I would say. Now you can actually improve the process by doing one-shot learning. So in addition to the question, so would you say this movie review is positive or negative? You add one sample answer. I love that movie, means it's positive. Then you ask your question, your prompt. I hated the movie. Then the model will tell you negative. Okay, so that's something you can do again quite easily using the same notebook. So you start with the same input where you give the context, the prompt, well, the question, and actually the answer there. And then you give another question, another prompt. And when you run that, you will get the answer that is coming just below. Yep, that's it. So the last few lines here to read the term NVIDIA, blah, 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 is actually the output from the one-shot example. You can, of course, extrapolate and do few-shot learning. So here you've got an example of few-shot learnings to actually perform translation. So remember, that model has not been trained for performing translation. So what we do is, if you look at the input user, we give a few sentences, Polish, English, Polish, English, Polish, and then we will ask the answer in English, right? So we do like two-shot learning. Actually, that's English, French, English, French, English, French, sorry. So we give a couple of pairs, for example, we run a model, and then we wait a little bit. So the model is hard at work now, and it will give you the answer, the translation. So remember, again, that model was not trained for that task. It's a text generation model, not a text translation model. And even so, it was able to do that. That's something you can install at home and play with already today. Right, so it still begs you one question. Prompts. How do we engineer? How do we design our questions, right? Actually, it turns out that the way you ask the questions to the model will have a lot of impact on the quality of the output. So if you look at the top right here, we've got 3 different prompts. DirectX is developed by, someone released the DirectX, and then for one, DirectX is created by. So the 3 questions, the 3 prompts have the same meaning, right? And we know that the answer should be Microsoft. Well, the 3 different ways to ask the model will give you actually 3 different answers. So for the first prompt, the manual one, it will tell you that it's Intel, which is not correct. For the mined and paraphrased one, it will give you the right answer, Microsoft. But the following answer will not be ordered in the same way. So also just changing one word or making substitution or removing a word or adding one into the prompt can actually change a lot the accuracy. And so if we just change in by at into that prompt, we get an accuracy increase of 23%, which is huge because you just change one sentence. So finding the right way to design the prompt engineering manually, it's something that can be task consuming and that can have a lot of impact on your model. For instance, if you have an LLM, like BERT or GPT, and you just ask it, what is the yellow part in an egg? It will tell you that it is the part that is suspended in the center of the egg, which is correct, right? But it's only one possible answer, and that's probably not the answer you were expecting to, because it depends on your context, right? So if we're able to add a bit of context, a bit of additional information to the prompt, the question, then that will drive the LLM to the right conclusion, the right outcome. And if the context was nutrition, it will tell you that the yellow part in an egg is the yolk. It contains the most fat, cholesterol, and protein. If it was healthcare, you would have that answer, or if it was culinary, you would have that answer there. Okay, so the only thing we need to do is actually not to care about how we ask the question, but how do we add context to the prompt. That we do with prompt learning techniques or p-tuning. So we want the model to learn automatically what is the context. So we just need to show the model hundreds of samples of inputs and outputs that will come into the domain prompt there. So the domain prompt will be divided into the task name and the input text. And the task name will be augmented with some tokens there. And those tokens associated with the input text will be put into a specific embeddings, right? That will be fed to the original LLM. We did not touch that one. So what we're going to do when we do backpropagation, we are just going to update the models here that will generate the tokens. So, and this model is typically an LSTM, so it's very small and very easy to learn. So what we do at the end of the day is we add an auxiliary model to the frozen LLM so that it will add context to the prompt, which will drive the LLM to the right direction. And because we do not retrain the LLM, we do not touch any of the billions of parameters there, but only the LSTM model there. It's very fast. You can retrain, you can do prompt learning in a matter of hours or days instead of weeks or months for an LLM. To show you how efficient it is, if you are able to do the best prompt or best fine-tuning manually for your model, using prompt tuning gives you actually the same performances, but you did not need to spend weeks or and days on fine-tuning yourself the model, right? You just need to retrain an auxiliary model that will give you the same accuracy. So that's the green line prompt tuning. And what does it look like? The dataset for p-tuning or prompt learning, that's just a JSON file, right? So you just have for each record, just the name of the task. So I had sentiment analysis, sentence, that's the input. And then you've got a label here, the desired label outcome here. Right, so you need just 100 of those. And of course, this line will depend on the task that you want to generate. If it was translation, then task name would be translation, sentence will be a sentence in English, and then you've got translation, then you've got the output in French or something like that. So very easy to design, very easy to use. Now, just to wrap up, we've covered a bit of big NLP or LLMs. We've seen that actually the more data you can use, the better it is, because the model will be able to, the large model are able to take advantage of it and become generalizable. Training an LLM doesn't take, well, it can be done quite quickly, especially if you limit yourself in the terms of number of parameters. So in 3 weeks' time, you're able to generate a text, an LLM for French and Spanish. There are some techniques you can use to limit the memory footprint and maximize the throughputs and the performances of the model using tensor parallelism and pipeline parallelism, for instance. But all of that is actually very easy to do if you go with NeMo Megatron, which is our accelerated framework to train LLMs. Right? So we provide pre-trained models as part of Megatron, like GPT, like models, MT5, T5, and soon we'll have Bloom as well. Megatron will come with tools for data curation and for training, making sure that you will always converge, which is not a given when you play with LLMs. It's optimized for multi-GPUs infrastructure, like DGX SuperPod. And we could train from scratch a 20 billion parameter in less than a month. Right, so that was really from scratch, not using pre-training. But with Megatron, you can use much more than that. So it's basically coming in 2 different containers, right? One for training and one for inference. So those 2 containers will actually give you guaranteed convergence recipes and also some sample application for chatbots. It will come with tools for distributed pre-processing for giant datasets, so data curation, deduplication, tokenization. Good tools for hyperparameter tuning and model navigation, so making sure that you use the right hyperparameters to train the model and finding the right architecture for you. You can use distributed training, so split the model across multiple GPUs and multiple nodes. And you've got also tools to make distributed inference. So the models are typically too big to fit into a single GPUs. So using NeMo Megatron, you're able to split the model across multiple GPUs as well. Right? So that's really an end-to-end framework that will take care of training and inference and dataset generation. You can scale up to thousands of GPUs very, very easily. And you have recipes for GPT-3, T5, and T5. GPT-3, we've got recipe for up to 1 trillion parameters if your hardware allows it. Now, you've got many, many pain points, actually, when you start playing with LLMs, and Megatron help you address those problems. So, as I mentioned, data curation and pre-processing, that's something that's there. Multilingual support comes with Megatron. Got an hyperparameter tool to find the right optimal hyperparameters. Got verified recipes for LLMs. Got plenty of scripts to run on premises or on cloud as well. There is tools to and techniques to optimize the inference, like quantization. Yeah, we've got full stack support for FP8, which is a new standard for precision. So instead of FP16, high precision, you can go to FP8. So that gives you better range, dynamic range than integer 8, but way faster than FP16. And yeah, so we also have, if you don't want to install Megatron and deploy this architecture yourself, we also have an API version called LLM Services that is currently on early access. But there we provide you models already for training. You just need to bring your data set or your prompts for P learnings, and you can play with T5 and GPT-3. Yeah, and the use cases that comes out of the box, that's summarization, paraphrasing, and some content generation, which comes with a nice little web interface. But yeah, don't want to go too much into details there. So we've covered a lot, and I've got a small assignment for you before we get to the Q&A. First of all, to get you started, I invite you to download the SDKs from our catalog. So the catalog is called NGC. NGC is NVIDIA GPU Cloud. So that's our repository for SDKs and pre-trained model. And you can look for NeMo, and then you will have a model card will explain you how to install it. It's very, very simple. You can either use Docker or pip or conda if you want to install that. And you can also apply for the NEMO Megatron open beta if you want to play with Megatron. So it's open beta, meaning that if you go to that website, when you apply, you will get automatically approval and an email telling you how to download it. You can also play with some of our LLM that we put on Hugging Face. For instance, the GPT 20 billion is available on Hugging Face. If you go there, you can download it and start playing with the inference server right away. But if you want to learn more and the latest development, and we have a lot of new things coming in the next few weeks, I invite you to register to our NVIDIA GTC. So that's our conference on AI and the metaverse. So of course, we cover AI, deep learning, NLP, LLMs, but also digital twins, robotics, and many other applications. And we've got talks for students and academics as well. So we've got here a couple of QR code. If you wanted to register to the GTC, you've got the shortened link there, and I'll put something in the chat as well. So yeah, that's it for me. Thanks for attention, and I'm happy to take questions now.
Okay, all right. Thank you so much for your presentation, Dr. Johan. Now, that is very useful information that you have presented today. So right now we are at the Q&A section. Please feel free to drop your questions below the chat box or comment box. Okay, let's get started. Oh, now we have a few comments and questions. Okay, I will read it out. Okay. It is very interesting to see the performance of Triton interface server. We need to take some time to look for and play with it.
Sure.
Yes. Okay. Okay. We were going to start with our first question. Okay. From Kun Akapok. Deep learning is fascinating. However, there are several challenges in training language models in Thailand. One of which is the randomly challenging of word meanings by Gen Y and Gen Z as they watch viral videos and mimic that what the person in the clip say to express their feelings or situation in their conversation, mostly found on Twitter. If you were Thai NLP developer, do you have any strategies or tools to overcome this challenge?
That's a very, very interesting question. Every language comes with their own challenges, you know, so English and Thai and Vietnamese and Bahasa Indonesia, they all come with different challenges. In that case, I think it's a matter of collecting enough data to augment your training data set and take that into account. So that's where I would start. I try to capture as many occurrences as possible for those particular sentences. Yeah.
Okay. Okay, our next questions are from Dr. Panarat. Okay, thanks for very deep explanation, and I have a quite simple questions to apply in NLP or conversational AI. It is quite difficult and challenge of getting the model to recognize the nuances of the Thai language. Any recommendation to deal with this challenge?
That's a very good one again. So most of the models have been designed with English in mind, right? The most obvious reason is most of the data is in English, unfortunately. But there is a new wave of models coming soon, and like Bloom, actually, that is multilingual, and I know that they've got good performances for Thai, and that's something that you are going to support in NEMO Megatron in the next release. So I would have a look at Bloom now, and I would play with it, and if it fits your needs, then stay tuned, because we are here to help you accelerate that. Something else you can have a look at is the tokenizer. So every language should have its own tokenizer, and well, I forgot which one is the best for Thai now, but I'm happy to come back to you. That's something I would have a look at. So either the model and or the tokenizer should be investigated. There is, I know it's a bit vague, but unfortunately, it's a very, very hard topic. So there is no definite recipes. It's more art than science.
So, okay. Another questions from Ms. Kun Akapov. One more questions as an experienced developer, do you have any short advice for new ML or deep learning students on how to prepare for future trends? What will be popular or transform the world in the next 10 years?
Oh gosh, if I knew that, I would be rich. Okay, so I think the best advice I could give anyone starting in deep learning and machine learning is to try things by themselves and to fail, right? Because when you break stuff, that's how you learn how to fix them and how to get more experience. I would not tell you how many things I broke down when I was a student, but don't worry about that. And for the future trends, well, we know we are collecting a lot of data, and we see that the models are getting bigger and bigger. But there is something new coming, which tries actually to get the model as smart while keeping the size quite small. So if you look at the latest work from Meta, for instance, they're able to get very good models with a few billion parameters. But that's for text generation. If you are looking for the next big thing, so LLM, they are the basis of generative AI. Right, and the GTC will be all about generative AI. That's huge. So using LLMs, the same models I showed you, you can start generating video, audio. You can start generating movies. So that's where I would go right now. Investigate how you can apply LLMs, understand the foundation, and apply them for multimodal models. Definitely, that's the future.
Okay. Thank you. Thank you so much. Okay. The message from Dr. Panarat, there are a lot of things we can play and learn from NVIDIA's tools. Thanks.
Yes.
Okay. Okay. Are there any questions? Okay.
I was going to say, if you've got any questions or any ideas, feel free to reach out to the NVIDIA team. I'm always happy to chat about AI and see how we can help.
Okay. Okay, are there any questions? So I will check to the comment box on the Facebook. Okay. Okay, if there aren't any questions, I'd like to thank you, Dr. Johan, for today's talk. And we hope you come back as our speaker again next time. I really appreciate it. Okay.
Sure. Thanks a lot for the invite. And it was really nice to be here. Thanks a lot.
So that's it for today, guys. Thank you, everyone, for attending our 4th TikTok 2023 AIEI NVIDIA. We hope to see you again in the next episode. Please stay tuned. Have a nice day and goodbye. สวัสดีครับ
Thanks so much. Bye.
สวัสดีครับ